I left off with the limit of a rational function. I did it in the variable h on Friday. Let's go ahead and take a limit in the variable x, and this will be as x approaches 0. The function I want to consider is 3x squared plus x, and this will be divided by x cubed plus 2x, like that. So I'm still in this situation where I have a rational function. I can't plug in 0 because 0 is not in the domain of this function. 0 sets the denominator equal to 0. But what I can do is I can factor an x out of the numerator and the denominator. So this will be equal to the limit as x tends to 0. And I will write this as x divided by x times the fraction 3x plus 1 divided by x squared plus 2. And what I was saying on Friday is that I can split this up and say that I can take the limit as x goes to 0 of just the function x divided by x and multiply by the limit of the function 3x plus 1 divided by x squared plus 2, again as x goes to 0. And like I said on Friday, this first limit is going to be equal to 1, and then the limit as x approaches 0 of the function 3x plus 1 divided by x squared plus 2. I do have 0 in the domain for this rational function. So my evaluation rule says I can just put x equal to 0 in the formula. I will have 3 times 0 plus 1 divided by 0 squared plus 2. And the answer will be 3/2. Oh, excuse me. Sorry. Too early for my algebra skills today. Let's say that is 0 plus 1. That's 1 on the numerator, 2 on the denominator. That's 1/2. Excuse me. So, I don't want to be doing this every single time, right? What if instead I was taking the limit as x goes to 1 and the function was x minus 1 divided by x minus 1? Every single time I have duplicate roots like this on the numerator and the denominator, it's not difficult to see that I will get 1 as the value for that limit. So, I'm actually going to impose a new rule as follows. So I'll call this the removable discontinuity rule. And here it goes. If the limit as x approaches a of f of x exists, right? So if I have a function f of x, the limit as x goes to coordinate a exists, and f of x and some other function g of x are the same. So if f of x equals g of x everywhere except x equals a, then the limit as x approaches a of g of x exists and is equal to the limit of f of x as x approaches a. So in pictures, what's going on is, let's say I have the function g of x, and it's some rational function. So it might be doing some curve, and then there's a hole, and then the function keeps going. If I can figure out what the graph of this function looks like without that hole, I'm allowed to use that formula instead. So this is implicitly what I'm doing when I say something like g of x equals x divided by x times 3x squared plus 1 divided by 2x minus 2. F of x equals 3x squared plus 1 divided by 2x minus 2. So f and g give exactly the same results so long as x is not equal to 0. I can use my formula for f of x to calculate the limit instead. So the limit as x tends to 0 of g of x in this example is the same as the limit as x goes to 0 of f of x. It's a handy rule.